Okay, deleted by somebody. Why? Okay, so if it is deleted by somebody, even I could not find it from my account also. So from now onwards, I will download it and I will upload it. If after that, if somebody somehow deleted, then I will take action. Right? Okay, so today I will start my lecture. So good morning, one and all. Okay, I hope that all of you can see the screen. Okay. I will start with one question. Basically, this question was asked by some of the students. Can we use double integral to evaluate the area of some region? Answer is yes. If we integrate the constant function fxy equal to 1 over a region D, then we get the area. How? All of we know that by double integration, what's the geometrical interpretation? Suppose f dx dy over certain region. Its geometrical interpretation is that if f is non-negative and d is some bounded region, and if it is integrable, then we can say that by double integration f dx dy over d, its meaning it's a volume. It represents the volume of the graph of the function below the region. Okay, so whatever the portions it is coming, this three-dimensional part, it's particularly volume. So what is that? The region, whatever V is set up on x comma y comma f here. F is equal to, you can say z. So whatever the region it is coming, whenever x comma y belongs to your T, so this three-dimensional region it is coming, as you know that function is non-negative, so naturally its graph lies above the xy plane, right? So whatever the portion it is coming, its volume is represented by the double integration. Now if we look at the function to be constant function, and that means what ultimately it happens to be 1 dA. dA means dx dy. It is like the area of D. So sometimes we call it A of D, means area of D. Note that for a solid cylinder, if we take a solid cylinder with base D and height 1, it has volume AD into 1. That means what? That means ultimately it's AD. But we can also write its volume as by the definition of double integration, or interpretation of double integration is like that. So in both way we can just say the same thing. Okay, here one dimension is less. Ultimately, it gives the area of D, that particular region. Here, if we again, we can also think as its volume, right? Okay. So now, one interesting fact, we can have some estimates of this double integration. Whenever we know that the f integrand function is bounded in between m, small m, and capital M for all x comma y in D, then m of AD is less or equal to double integration dA less or equal to m into capital M into, that's the upper bound, into area of the D. Okay, so this is very easy to give the proof. And this is the lower bound for this particular integrand, and this capital M is the upper bound for this particular integrand f. Okay, so we can tell it is in between a small m, lower bound of f, into area of the region of integration AD, and capital M into area of D, that is the upper bound for the integral, right? Okay, now question is that can you estimate this integral e to the power sine x into sine y? So dx dy, where D is a region, it's a circular disk with center is origin and the radius is 2. What is your D? This is say for example, this is your 2, that means this part. Okay, so this is your D. It's 2 comma 0. This is your D. Okay. Now whether we can estimate this thing or not. Yes, we can estimate it. We can use the previous property. So all of we know that whenever sine x is real number, then it is minus 1 less or equal to sine x less or equal to 1. And at the same time, cosine x is also right that like that. So we can write minus 1 less or equal to sine x into cosine x is less or equal to 1. Okay, so we can get it. So ultimately, whatever we can tell, 1 by e is less or equal to e to the power this sine x cosine x is less or equal to e, right? E to the power 1. Because sine x cosine x, so we can have this. This is basically your f. This particular thing is your f, right? So we can have 1 by e less or equal to f less or equal to e. This is your small m. This is your capital M, right? And what is the area of D? Who can tell? Area of D basically, A of D is nothing but pi into r square, means 2 square. That means what? 4 pi, right? Now using the property, using the above note, using the above note, we have, what we have? We have small m. What is small m? 1 by e into area of D, that means 4 pi, is less or equal to your f double integral over D, f dx dy. It is less or equal to capital M is E into AD. What is AD? AD is nothing but 4 pi. So we can have an estimate. We get it. So that means by this property, we can at least have some idea where it happens. Okay. So this is clear. Next, we like to introduce your triple integration. Just initially, I like to extend the concept. Then again, I will come back to your double integration certain parts. Okay, so triple integration, what is the notation wise? This is simple. Initially, we take a box, rectangular box, and function is fx, comma y, comma z, dx, dy, dz. Okay, so or we can write dv. And what is your b? B is nothing but a rectangular box. What is that? A comma b. This is the limit for x. C comma d. This is limit for y. And p comma q, small p comma small q. This is limit for z. So whatever the region of integration and whatever your function is f from b. B for box. First letter of b. Box. B to r plus. Initially, I denote the function to be non-negative. So that is why R plus is sometimes regarded as non-negative reals, right? So any function, its domain of definition is a rectangular box, right? Or rectangular parallelepiped, whatever you can say. So what is this? I think all of you understand. Suppose this is basically your P, A comma B, and let's say this is your X, this is your Z, this is your Y, and maybe Y is in between this thing. Okay. So if Z is in between something, then whatever we can have. So whatever the common portion, that part, basically this part is your box. Okay, rectangular parallelepiped. This part. This is a three-dimensional thing. Something like if we draw this thing, this particular. Okay, I have to be a little bit cautious here, and this thing, something like this part. Okay, so this is your box. Now, we like to develop the same way as we did in case of double integration. In case of double integration, whatever the domain of definition of the function, it's a basically square or maybe rectangular box. Sorry, just a rectangle, not rectangular box. In that case, it was just a comma b cross c comma d. And f was a function from r to r plus. So in that situation, graph of the function, it is a collection of all x comma y. This is domain of definition, comma f, x comma y. So this part is the graph of the function where x comma y belongs to your r. Here, this particular thing is from the box, right? Okay. But here, if you try to visualize the thing, so whatever the graph of the function, graph of f, this is by the definition, graph of f is x comma fx, right? So what is your x? X means it needs three dimension, x, y, z, right? And what is fx? Fx is your w. Say for example, w is your fx. Uh, this is ultimately, this w is f of x comma y comma z, and where x comma y comma z belongs to your box B. So this is the graph of the function. Now, whatever the difficulty here we face, can we visualize this? Because this is, it's a subset of four dimension. It's a subset of R4. How many dimensions are there? 1, 2, 3, 4. So anything which is beyond three dimension, we cannot visualize that thing. Okay. So geometrically, we have to tell it is also something above that rectangle, three-dimensional region and below the graph of the function. Okay, so but graph of the function we cannot visualize because it's a four dimension. So whatever the real difficulty in understanding the geometrical idea, therefore we cannot give geometrically this thing, but we can at least we can intuitively we can understand that it is ultimately it becomes a four-dimensional thing. So once something is having four-dimensional thing, if we calculate the volume, so there is no term dedicated for anything which is beyond three dimension. So we call it to be volume. It may be if it is five dimension, then also we call it volume. Six dimension, then also we call it volume, and so on. Right? So again, I back to the very starting point. That means whenever we are dealing in real line, then whatever it is called, it's a length. Whenever we are coming on plane, we are calling its area of a region. Whenever we are coming to a space, that means geometry of the double integration, it suggests volume. Volume means 3 dimension. Okay. Now, whenever we are coming to a space which is bigger than 3 dimension, then also we call it volume. In general, we call it volume. So ultimately, we get the volume um, uh, below the graph of the function. Above your 3 dimensional region, whatever it is coming, it will be a 4 dimensional thing. So 4 dimensional thing, whatever it will be coming, that is your W. So its volume, that means by triple integration over your box f dv, f of x comma y comma z, I can write, or if there is no confusion, then we may not write it. Now this is going to be equal to volume of, I call it volume of W, where this capital W is collection of all x comma y comma z comma small w, where x is in between a to b, y is in between c to d, and z is in between p to q, and w is less or equal to f x comma y comma z less or equal to w. Okay, so this part, whatever it is coming, this is under the graph of the function, this function under this graph, and above the box, whatever the box here, b is what? B is this box, this thing, right? Okay, this is the domain of definition. Okay. Okay, so we get like this thing. Triple integration by means this is also volume of a 4 dimensional region, because there is no dedicated term which is available for dimension higher than 3. So we call it as volume, right? Okay. So geometrically also you understand, and the same way, if iterated integrals exist, then we can find by means of the iterated integral. How many iterated integrals are there? Suppose f is integrable, and one of the iterated integral exists, then we can find the triple integration by means of that iterated integral, right? Okay, so what is that? One of the iterated integral is a to b, c to d, p to q. This is one. F, x, y, z. This is first dz, because z is running from p to q. Then dy, y is running from c to d. Then dx. Okay, so how many iterated integrals are there? Who can tell? Ankit, Ankit, you are there?
Yes, sir.
Please tell.
Sir,
How?
there there will be six iterated integral.
Very good. Okay. Please mute, mute.
Okay, sir.
So, how many choices for this? This is how many choices? Three. How many choices for this? This two. How many choices for this? One. So, total number of choices. Total number of iterated integrals is six, right? Very good. 3 into 2 into 1. That is 6. Okay. So once we write in terms of iterated integral, then we have to be little bit cautious writing dx, dy, dz. So you cannot change that, like in the case of double integration. In case of double integration, all of you know, suppose I am taking this thing 0 to pi, some function f of dx, dy. That means what? I cannot write the same thing like 0 to pi dy, dx. These are different meaning. Here its meaning is x is running from 0 to pi, y is running from -1 to 1. Here its meaning is y is running from 0 to pi, x is running from -1 to 1. So this you cannot change this dx dy at your own. Okay, so you have to see the given question, and then only you have to write it. So that means what? Whenever we write the iterated integral form, if it is the case of double integration or if it is the case of triple integration, then we have to write it very judiciously. And if we write in case of double integration, say for example, if I write over some region d f dx dy, this has the same meaning over d f dy dx. There is no issue. You can write dy dx or dx dy, there is no issue. Meaning is same because we are writing it as double integration. So very careful you have to be. Once you write in terms of triple integration, say for example, if I write in terms of triple integration over box B, if I can write dx, dy, dz, you can write dz, dy, dx, no problem. But once we write in terms of iterated integral, we have to be careful regarding the order of dx, dy, and dz. Because from this order, we have to understand where it varies. Okay. Now the question comes how we integrate it, how we evaluate iterated triple integration. So here the answer is very simple. First, what we do, we like to find basically this part, dz. With respect to z, we like to integrate f x comma y comma z, keeping x and y constant, and then putting the limit for z from p to q, right? So ultimately, we are getting some functions of x and y. Then we are in a position to uh, integrate this thing with respect to y, keeping x as constant, and we have to put the limit for y, that is c to d. Then ultimately, we get a functions of x. So at the end, we have to integrate with respect to x. So what is that? That I can use some different color. So that function we have to integrate with respect to x. So that is a function of x only. And we have to put the limit for x from a to b. So that limit is nothing but your, ultimately we are getting a constant, that is your volume. That is ultimate triple integration, right? So in this way we calculate it. Okay, so I like to give one example here. Uh, so that you can have some uh, more clarity. Today I say that it is example number, it is maybe example number 2 because already I gave one question, one or two questions. Okay, so we have to evaluate with respect to some box x, y, z square. This is a little bit simple, dx, dy, dz. So what is your box? Box is 0, 1 cross -1, 2 cross 0, 3. Okay. So this is your triple integration. So I have to write it. This is as one of the iterated integral. Look at that. This function is continuous. So there is no, so it is integrable. So we can use the Fubini's theorem. So once it is integrable, it is equal to even if it is continuous, we are very strong. We are in a very strong situation. That means all the iterated integral will exist and they will be same as that of your triple integration, right? So this is parallel in case of double integration. So I can find one of the iterated integral like 0 to 3 and -1 to 2, 0 to 1. This is x, y, z square. I write dx, dy, then dy, then dz, right? Sorry. So 0 to 3, minus 1 to 2. So what is this? We have to integrate with respect to x, keeping y and z constant. That means it is x square y z square by 2, and limit for x equal to 0 to 1, then dy. I can make it here, then dz. Right? So what is this? This is nothing but 0 to 3. This part is um, minus 1 to 2. What it will be? Okay, so I can give one step jump here. It's very easy. So this will be y square z square by 4. Y is equal to minus 1 to 2 dz. Okay, ultimately. So this will be 0 to 3 t z square by 4 dz. And this will be your z cube by 4, 0 to 3. So ultimately it is 27 by 4. Okay, so all of you understand, this is simple. Okay, then I'll be coming to some change of variable in double integration. Then again, we'll back to triple integration once it will be necessary. Change of variables. Okay, so particularly, I like to give some special condition. Suppose our target, before coming to general case, in case of change of variables, particularly if I just like to tell, uh, say for example, x sine x square dx, and 0 to, say for example, pi. So in order to integrate it, this is in case of single integration. So all of you understand that we have to put y square equal to, it is suggested, this y is equal to x square. This basically change of variables. We put x square in terms of y, and then we change it, and then we find it, right? So how that means x dx, twice x dx is equal to dy. That means x dx is basically dy by 2, right? Then what we do, we change the limit also. Basically, we change the limit in this case. Whenever x equal to 0, y equal to 0. Whenever x equal to pi, y equal to pi square. And then what we do, x dx is equal to dy. That means sine y dy, right? So now we are in a very comfortable situation to integrate it. This is the case in case of single integration. But in case of double integration, the situation is not so easy. Suppose sometimes uh, some region is there, f x y dx dy. In order to integrate it, we can see that if we change the variables x to some x, y to some other variables u comma v, then the integration becomes very easy. But how to do that? That is basically our target today. So in case of double integration, and similarly for the triple integration, if we have to, in order to evaluate the triple integration, we have to do that kind of thing. So how we can tackle this, and in what kind of situation we are getting advantage. So I am sure that particularly change of variable in case of single integration, you are very good, because uh, last few months, maybe last 6 months, you are very much busy with so many difficult exercise doing like integrations and different type of exercise while you preparing for IITs and NITs, right? So, but here the situation is a little bit different. But I like to hear from you whether you are habituated in case of double integration or triple integration. So I have allowed 2, 3 students to talk. Ankit is one of them.
Hello, sir. Am I audible?
Yes, Aditya.
Yes, sir. Yes, sir. Sir, in our 10 plus 2 system, there was no double or triple integration.
Yes, yes,
It's new
yes.
for us.
Yeah, okay, so you understand everything,
Yes,
whatever
sir.
I
Yes,
told.
sir. Yes, sir.
Okay, try to understand the developments and other things, so that I repeatedly try to say that all of you try to attend each and every lecture. Okay, I gave a very nice book. The Marsden, Tromba, and Weinstein. So one of the author, do you know? One of the author is Fields medalist. So that is equivalent to Nobel Prize in because in mathematics domain there is no Nobel Prize. So Fields medal is the topmost award. It is equivalent to Nobel. So this is in fact, if you read that book, this is a very nice book. So you are having very nice book. One option. Another option, you are having a definite lecture note. It is prepared by me. I already uploaded. And another thing, third thing, it is I am writing as board work, so it is having your supplementary thing. And maybe fourth is my lecture. So there are, and I prefer to go by this: my lecture first, and then my writing, and then my lecture note. It is typed in LaTeX, and then you can go for the book. Okay, so these are the four things you have to just read very attentively, or you have to read in between the lines. Okay, so suppose this is line, this is another line, there is a gap, this thing is white space, right? So you have to read not the lines, but read between the lines. That means you have to understand the thing. Then everything will be very clear to uh, each of you, right? So all of you understand the target. Target is sometimes, if we see, say for example, if I take this kind of domain of definition, suppose this is your origin, and this part is your R, uh, and this is x square plus y square equal to 1. Okay, this is your x-axis, this is your y-axis. So this is your region of integration, or maybe like this particular thing. Okay, so this is, say for example, this part is x square plus y square equal to 1. This part is x square plus y square equal to 4. And this is your region of integration, this R. Okay, so if we have to write in this way, and we have to evaluate certain integration, and maybe this is your R2, this is your R1. So I can write in terms of polar coordinates. So in this case, if we try to, you are having two options. R1 you can write in terms of type 1 or type 2 region in the rectangular coordinate system. Similarly, you can write for R2 as type 1 and type 2 region. But at the same time, if we try to write this part in polar coordinate system, all of you are habituated. So this is what, this is very simple way we can write. It is r comma theta, where r is 0 less or equal to r less or equal to 1, and theta is 0 less or equal to theta less or equal to twice pi. It is full rotation. Okay. Now, what is your R2? What is your R2 particularly? R2 is r comma theta in terms of polar coordinate system. So it is r is 1 less or equal to r less or equal to 2, and theta is 0 less or equal to theta less or equal to pi. It is half rotation, not full here, whatever the region R2 is given. So we can see that, we can confirmly say that if we use polar coordinate system, then we can easily integrate the integrand function, right? And whatever the transformation for that, it is r square equal to transformation is r square equal to x square plus y square. So how we get it from this, r x equal to r cos theta, y equal to r sin theta. So you understand theta is having the full rotation, and r is basically the radial vector, right? So whatever, if we try to draw the picture, say for example, this is your x and this is your y, initially your Cartesian coordinate system, and this is your px comma y. This point, uh, this is basically y, this part is x. Okay, so what is this particular part? This is your r, and this particular thing is theta. And I can write this point as p r comma theta, right? So this is the angle, 90 degree. Okay, now hmm, now we like to change polar coordinate in double integration. Okay, so what we have to do, and why we have to do those things, I like to write it. If f is continuous on a polar rectangle r given by, I write in general, given by 0 less or equal to a less or equal to r less or equal to b, and alpha less or equal to theta less or equal to beta, where 0 less or equal to beta minus alpha less or equal to twice pi. Then double integration your r f x comma y dA or dx dy. This is going to be equal to alpha to beta and a to b f r cos theta, x is equal to r cos theta, y equal to r sin theta. Here, this is not just dr d theta. We have to write here r dr d theta. D theta. Some r is coming. This part is coming. One factor. Instead of dx dy, dx dy, we replace dx dy by r dr d theta. Okay, so this thing we have to say. Okay, why this thing is coming? So I think it is not very tough to visualize. I like to draw the picture, then you understand. Okay, so basically this thing, this part is your dA, small area here, and this particular thing is dr, and this thing is theta, d theta. right? So whatever it will be coming, it is r d theta. This thing is r d theta. So if it is infinitesimal distance, area part, then ultimately it will be coming r dr d theta. So this dx dy, initially whatever dx dy, the area element, it is replaced by r dr d theta because of this thing. This thing is coming r d theta. This part is basically dr. So ultimately, if we multiply it, so this is not exactly a rectangle, but it is. See, if it is very small, then you can think of its area element is like this thing, r dr d theta. Okay, so uh, hope I you understand. Then I give one example, very simple, and then uh, another example may be a little bit difficult. Example 3. Suppose we have to evaluate over R 3x plus 4y square dA, where this is basically R2. I draw the picture, same picture again. And this is your R2, this part. And this is x square plus y square equal to 4. This is x square plus y square equal to 1. Okay, so this part we have to do. So we can calculate by means of your Cartesian coordinate also. There is no issue, but it is little bit difficult. But I can write this thing as in terms of polar coordinate system. So whatever it is coming, so it will be coming to 0 to pi, and r is 1 to 2, 3r cos theta plus 4r square sine square sine square theta into, I have to write r dr d theta, because dx dy is replaced by r dr d theta. So this is basically we have to do. So if we do it at your own. So this part is easy. Okay, so ultimate answer I write it. It will be, I have just solved it. It is 15 pi by 2. So you please check, because all of you know. So no need to waste time here. Okay, then I am having 9 to 9:45. Okay, I like to give another important exercise that is related to Gaussian integral. All of you know, this is one of the application also. You can tell e to the power minus x square dx, integration minus infinity to infinity. This is known as Gaussian integral. So it is very interesting integration, and its value all of you know. Now, how to do that? Using double integration, we can find this integral. This is example 4. Okay. Now, we start with our double integration, simple double integration. What is that? E to the power minus x square plus y square dx dy over dA. What is dA? dA is nothing but x comma y such that x square plus y square is less or equal to a square. Okay, so this I like to find. So note that whatever the domain of definition, this is something like this. Maybe this is x square plus y square lesser equal to a square. So this part is lesser equal to a square, means inside circle and inside the circle, right? This is your dA. Particularly, it depends on A. If A is large, then your circle will be large, right? Okay, so the basically the integrand function and the domain of definition suggest us to use the change of coordinate, means Cartesian to polar coordinate system. So put x equal to r cos theta and y equal to r sin theta. So in this case, your r will be greater equal to 0, and and dx dy, it will be changed to r dr d theta. Okay, and theta will have the full rotation, twice pi, and r is 0 less or equal to r less or equal to a up to the radius, right? Okay. So we can calculate this double integration I as particularly 0 to a, 0 to 2 pi. So ultimately, if we look at this, e to the power minus r square r d theta, I have to write theta first, then dr, right? Okay, so what it is coming? So we can write instead of theta, so it is 2 pi is coming outside, and 0 to a r e to the power minus r square dr. So it becomes very easy, this integral. So ultimately, it is pi into 1 minus e to the power minus a square if I do the integral. So this is maybe it is 1, question number 1. Okay. What I do, my target is to find the region of integration is whole real line. See, minus infinity to infinity, and it is the power minus x square. But here, whatever we are considering, the domain of definition, it's a circular disk, and the disk particularly dA, it depends on the value for a. If a is very large, then it will cover the whole plane, right? That means minus whole plane means what? This is something like minus infinity infinity. This is your x cross minus infinity infinity. So it will cover them. So now letting a tends to infinity. So a is very large. Then what happens? Then one will become, what one will become? Equation number 1. This is a, in this particular thing, whatever the given integral, this is nothing but your R2, whole R2. That means you see, whenever A is very large, this A is very large, then it will cover the whole R2, means whole plane. So domain of definition will become R2. That means minus infinity, infinity, minus infinity, infinity. So it is e to the power minus x square plus y square dx dy. It was the original whenever a tends to infinity. This becomes, if we like to take the limit a tends to infinity, so this part is okay, I am writing limit n tends to infinity, sorry, a tends to infinity. That means pi into 1 minus e to the power minus a square. So it is nothing but this part will go to 0, because e to the power a square, a is very large number. 1 by e to the power a square, 1 by very large number, it goes to 0. So ultimately it goes to pi. So I think all of you are sure here. A tends to infinity. Okay. Now you see that what happens actually. Can I write this as minus infinity? It is continuous function, minus infinity to infinity, minus infinity to infinity. E to the power minus x square plus dx dy. Can I write this is as pi? So now you see x is varying from minus infinity to infinity, y is also varying from minus infinity to infinity. So ultimately we can we write that if we change this is nothing but e to the power minus x square dx this part minus infinity to infinity, and this part minus infinity to infinity to the power minus y square dy. I can write in, so this is your phi. So you see the same thing, symmetry. X is varying from minus infinity to infinity, y is varying from minus infinity to infinity. That means we are in a position to change the role of x to y and y to x. That means what happens? Minus infinity to infinity e to the power minus x square dx. It is same time twice. Its square is equal to pi. That means ultimately minus infinity to infinity, whatever we like to find, e to the power minus x square dx, it is root pi. So this is very, very important integral. Even if you try, all of you know the single integration. Even if you try to find this particular Gaussian integral, its value, basically pi, it is not easy to calculate in terms of single integration. If you use some beta gamma function, then again, or if you go by the standard rules in single integration, this is very difficult. But using the double integration and its change of variable system, we are in a position to calculate this integral in a very simpler way, and that is going to be equal to square root of pi. I think all of you understand this part. Again, I like to tell it. See, this thing, this is basically the thing, whatever from 1, if we take limit a tends to infinity. That means your region of integration becomes the whole plane, and it is like that. Okay, so I can write separately like e to the power minus y square dy, because y is running from minus infinity to infinity. X is also running from minus infinity to infinity. So you see the symmetry in the integrand function, that you can change x to y and y to x, so there is no issue. So ultimately it is this is 2 times, so minus infinity to infinity e to the power minus x square dx, its whole square is equal to pi. Right hand side we calculate it, so this part is square root of pi. Okay, done. So this is for up to today. In the next class, my planning, maybe next Thursday. So whatever the planning is to develop how to use uh, double integration, its change of variable, and we will again go to the triple integration and certain other properties of triple integrations. Okay, so change of variable is one of the important thing we have to learn, and it is also a little bit conceptual part. This much for today.